Hello everybody, how are you doing? Are you interested in learning about one of the greatest symbols of mathematics, pi? So a few weeks ago I did a stream in Twitch where I was looking through why pi is irrational. And I was following a book by Matti Lehtinen where he was going through the proof of Niven and Iwamoto. So it's a proof from the 1940s, 1950s that pretty much only assumes high school knowledge. And with it, you can prove that pi cannot be written as a quotient of two integers. So there's some kind of earlier proofs. Most famous one is from Lambert, which uses properties of the arctangent function. But those are like very, very, very technical. In a sense, they show that the arctangent of a irrational number. So the arctangent of a rational number cannot be an irrational number, and use that. But that proof is very complicated, very technical, and even in the original proofs there were some mistakes. So today I'm going to show the general idea of how to prove that pi is irrational with only using high school knowledge. I'm not going to go through all the details, but I'm going to tell you what you need to do, what kind of thing you need to calculate, and then you'll figure out all the details yourself. So I'm just going to go through the general idea. Right. So to see that pi is not a fraction, how do we reach this? So the proof is based on, in a sense, three steps. In the first step, you look at this kind of integral. So you integrate from 0 to 1. You integrate this polynomial 1 divided by the factorial of n times x to the power of n times 1 minus x to the power of n. And then you multiply by sine times pi of x dx. So you look at this integral, and here there's the pi here, which ties this to what we want to prove. So this integral appears so often, so let's call it I of n. So n is here any natural number, and we're going to look at what happens to this thing when n goes to infinity. So first there's kind of the analysis part, which is to note that this thing is first of all always positive. That's because the sine function is positive between 0 and pi, and then this polynomial here is always positive when x is between 0 and 1. And then the second thing to note is that all those integrands that depend on x, they are at most 1. So therefore, this has an upper bound. This cannot be more than 1 divided by factorial of n. So that's kind of one of the key analysis parts for this. A second part is that now we've estimated this integral. What we do next is we want to kind of calculate its precise value, and the precise value will involve pi. So we can actually see the following. So this I of n is going to be a rational function of pi. In a sense, it's going to be of this form. So C1 is some constant divided by pi, plus C3 divided by pi cubed, etc. You sum all the way to some C2n plus 1, so a further constant to the power of pi divided by pi to the power of 2n plus 1. And what is kind of the difficult aspect here is to show that all these C1, C2, etc., so C1, C3, all these constants, they are integers, so positive or negative numbers that don't have a fractional part. So if you have these two, you can then combine them in the following way. So if pi would be a fraction of two integers, like a divided by b, so a and b, we can assume that they are both positive. So if you do that, so if you assume that pi is a divided by b with a and b being integers and non-zero, you can actually assume that they are positive integers. Doesn't really matter. Anyway, so if you combine that with this formula up here that we had for I of n, you can then write that I of n is going to be, let me write it a bit more down here. So I of n is going to be C1 divided by divided by a times b plus C3 divided by b cubed divided by a cubed, etc., plus C2n plus 1 times b to the power of 2n plus 1, and divided by a to the power of 2n plus 1. But what you can here do is that you can then multiply all these fractions to have the common denominator, which will be a to the power of 2n plus 1. And then on top here you would have c1 to the power of c1 times b to the power of a to the power of 2n plus c3 times b cubed times a to the power of 2n minus 2, etc., all the way to c to the power of 2n plus 1 times b to the power of 2n plus 1. And this one is some integer, let's call it a, capital A. So it depends on n, it depends on a, it depends on b, and it has a to the power of 2n plus 1 on the bottom here. So this is kind of one of the key aspects. And let me actually erase, make more space. So in a sense, the main point of that part is to show that this integral that we had can be written as some integer divided by a to the power of 2n plus 1. And now, if we look at this original estimate we had up here, then we see we have some limit for this integer capital A. So if we plug this formula for in into this estimate here and multiply by what we have on the bottom here, we get an estimate that 0 is smaller than this capital A, which is smaller than a to the power of 2n plus 1 divided by n factorial. And this is true for all n. And n could be any positive natural number. And what you can actually see from that, so you can rewrite this in the following form. So a times a squared to the power of n divided by n factorial. And the factorial will grow much faster than any exponential with a fixed base. And you can see that, you can prove it by induction, but in a sense, what you can see is that when n is equal to a squared, then after that, when you add higher factors, then you will increase the bottom part much more than you start increasing the top part. So at some point, this factorial will kind of catch up with this a squared multiplied by itself, and after that it will like start growing much faster and faster. So in other words, this thing is going to go to 0 when n goes to infinity. And this is then a contradiction, because a here is an integer. Like, sure, it depends on n, but if n is large enough, so this small a is now fixed based on what we assumed pi to be equal to. So for some n, you can make this right-hand side smaller than 1. And that means that for that value of n, you would have some integer a, which is between 0 and between 1. So that's obviously impossible. So this is a contradiction, which then implies that pi cannot be rational number. So contradiction. So this is pretty much the general idea of the proof. The only thing that really needs to be shown is that up here, in this formula for in, so first of all, the formula, and second of all, why are these constants integers? So the first part is easier to do. It's in a sense a recursion. So you define, just to make notation simpler, you define a polynomial p of n of x. So that's the 1 divided by factorial of n, x to the power of n, 1 minus x to the power of n. And you define another one, which is kind of like this original integral, but where we differentiated this polynomial. So you define c of k is integral from 0 to 1. P of n differentiated k times. And then you have sine of pi x dx. Right there. And then turns out that C0 is the same as I of n. And if you integrate by parts, so you use the fact that sine of pi x is the same as 1 divided by pi squared 2 times derivative of sine of pi of x. So then this one you can always replace it by second derivative of itself divided by pi squared. And then you can use integration by parts, in a sense, twice, or you can use like Green's formulas or Gauss's theorem to move the 2 derivatives from here to here. And if you do that, you see the following recursion formula. So ck is going to be equal to 1 divided by pi derivative of, let me put it this way. So 1 divided by pi derivative of p of n of, so derivative of order k evaluated at 0 plus derivative of order k of Pn evaluated at 1 minus 1 divided by pi squared c of k plus 2. So this is the key calculation in this proof. And what we can also see is that this Pn is a polynomial of degree 2 to the power of n. So if you differentiate it 2n times, it's going to result in some constant. So if you put k equal to 2n, then this last one would be c 2n plus 2, where you differentiate it more than 2n times is going to be 0. So if you apply this recursion, you will see the following. So I of n is c0. It's going to be p of n 0 plus p of n 1 divided by pi minus p of n second derivative. Let me put it this way. There we go. Evaluate at 0 plus second derivative p of n evaluated at 1 divided by pi cubed, etc. And then you have plus or minus the last term. So 2n derivative of p of n 0 plus 2n derivative p of n evaluated at 1, and the whole thing divided by pi to the power of 2n plus 1. So this way you get the formula. And this kind of is part 1 here. So this above here is just a notation. And now kind of the last thing you need. So now you actually have a formula for all these C1, C2, etc. They are just this polynomial evaluated at 0 and 1, and you evaluate different orders of differentiation there. So the last thing to see is that all these derivatives are integers. And for that, I will leave it as a little exercise. So what you need to know is that derivative of k of p of n at x is an integer when x is equal to 0 or x is equal to 1. And once you have this one, you have the last step for this proof. And the way to prove that, there's several ways. One way is to literally just write what this is. Use the binomial theorem for this. So it's a bit of an advanced topic. But basic things. So there's a formula for the binomial. You use it. You calculate the derivatives, and you see that they are integers. Another option is to know that if you differentiate p of n, you are going to get a polynomial with integer coefficients. Let me actually write it up here. So if you differentiate p of n evaluated at x, it's going to be 1 minus 2x times p of n minus 1 at x. Right. And you can also see then that if you then, so you can first of all see that for any of these n's, pn at 0 and at 1 is going to be equal to 0. And then you can use kind of this recursion formula and an induction to see that if you differentiate kind of k times, you're going to get a polynomial times p n minus 1, a polynomial times p of n minus 2, a polynomial times p n minus 3, etc. And all of those polynomials will have integer coefficients. And all of these pn's, you would know that they have integer values at 0 and at 1 when there's no derivative here. So in that way, you can kind of recursively see that these polynomials and all their derivatives are integers on the border of this interval. So now you have like all pieces. So let's go again quickly how the proof goes. So to see that pi is not a fraction, you look at this integral up here, and you make an estimate that it's between 0 and 1 divided by factorial of n. Second thing is that you calculate an exact value for this integral, and you see that it's going to be a fractional, like a rational function of this form. So some constant divided by some power of pi, and you add a bunch of those together. And then you see that those constants are actually integers, and you do it by having, first of all, the exact formula for them. And you do that by, in a sense, integrating by parts 2 times always, using this notation here. And then noticing that these polynomials, p of n, and all their derivatives have integer values at 0 and at 1. This is something you need to prove by induction. So once you have that step, you can combine these 2 steps and assume, like if you then assume that pi is a divided by b, and a and b integers, you can see that this rational function can be written as some integer divided by a to the power of 2n plus 1. And then you put that formula in the estimate here, and you see that if you multiply by this denominator, you have an integer that's positive and has to be below this function that becomes smaller when n goes to infinity. So there will be some value of n that depends on this number little a. So some value of n for which this integer must be between 0 and 1, and that's impossible because, well, integers. So therefore, if you assume that pi can be written as the division of 2 integers, you get a contradiction. Therefore, pi has to be an irrational function. So there you have it. Remember to like and subscribe for more videos like this.